Good afternoon, ladies and gentlemen. In this short video, I'm going to go through your problems in your textbook on page 65, part of your homework. It's starting with number 34. Hopefully you can still see it because of the glare. So the first question is, calculate the acceleration of a ball that starts from rest and rolls down a ramp and gains a speed of 25 meters per second in 5 seconds. All right, so before we can talk about acceleration, we need to be really clear on what exactly is acceleration. So I'm going to give you a review on that. Let me see, I've got to get this and say new share. So complicated. Okay, so here we go. New share. Here we go. What exactly is acceleration? Let's say you have your driver's license, but you're really nervous about driving on the freeway. And you've got to go all the way down to some uncle past Fresno. And so for the first hour, let's say it's going to take you 4 hours to get there because you're being really cautious. And you had to start in Roseville. So the first hour, the whole hour, you went 55 miles an hour for the whole hour. Second hour, you got a little more brave and you put the pedal to the metal. And for the whole second hour, you're now at 55 miles per hour. Then the next hour, you're a little bit more brave. And now with more courage, you're going to press the metal to the pedal. And now you're going 60 miles an hour. And you guessed it, the fourth hour, you're finally confident in going the speed limit and you're going 65 miles an hour. The question is, what is the acceleration? How much did you accelerate? So let's look at the definition of acceleration. Acceleration is the change in velocity over the change in time. Okay, so what is the difference in the velocities? Remember, the velocity is a vector, just telling you south or north or east or west, but the magnitude, the actual size of the velocity is the speed. That's what's saying on your speedometer. So your final velocity, so let's look at the acceleration between hour 2 and hour 1. So your final velocity, you got up to 55 miles an hour, but you started 50. So VF minus VI, final minus initial, would be 5 miles an hour divided by how many hours? 1. So notice the units are miles per hour, and that's your acceleration. Well, let's look at this between the third and the second hour. Final velocity is 60 miles an hour, and your initial velocity was 55. So 60 minus 55 is 5 divided by 1 hour. What if we compare it between the third hour and the first hour? Your final velocity is 60, goes in here, 60 minus 50, that's 10, divided by how many hours? 2 hours. Between 1 and 3 hours is 2 hour difference. So again, it'll be 10 divided by 2. It's 5 miles per hour. And that's why we say meters per second squared, because I've got miles per hour, which is miles per hour squared. That's what acceleration is. All right, so let's look at the equation in the book again. Let's see, new share. All right, let's look at what they're asking for you here in the book. Number 34, takes a bit for it to come up. It says, calculate the acceleration of a ball that starts from rest. What does it mean it starts from rest? It means that the velocity started at 0. So my initial velocity is 0, and I usually put a line through it just to make a distinction between an O. So it starts at 0, and then it gains a speed of 25 meters per second. 25 meters per second. So V final is 25 meters per second. And then they tell you the time. They tell you the time is 5 seconds. So the time, I put delta T is 5 seconds. All right, so what was that acceleration equation? The acceleration equation, this over here, acceleration equation is, what is the change, my shorthand, change velocity over the change in time. This is a Greek letter delta, it's like a little triangle, it just means the change. So what's the change mean? It's always final first, V final minus V initial, and then it would be T final minus T initial. But they already told us the delta T is 5 seconds. So that's 5 seconds. I put sec because my little S's look like 5s. Not very clear. Okay, so V final I know is 25. So 25 meters per second minus 0 meters per second, all over 5 seconds. All right, 25 minus 0 is just 25 meters per second over 5 seconds. So 25 divided by 5 is 5. I end up with meters per second squared. Now, why is it meters per second squared? Well, let's look at just the units here. All right, I have meters per second divided by seconds. Well, remember dividing fractions. I'm going to put an S over 1 because anything can be over 1. Dividing fractions, same thing as multiplying it by its reciprocal. So this is the same thing as M over S times, I'm going to flip this guy over, 1 over S. Okay, that's the same thing as dividing fractions, same thing as multiplying it by its reciprocal of the one in the denominator. So what is that? Okay, now I multiply my numerators. M times 1 is just M. And then S times S is S squared. S squared. So that's why I know my acceleration here is 5 meters per second squared. Okay, maybe this is a little too big here. All right, there we go. So that's what they're asking for. All right, so that's number 35. No, okay, that was number 34. Number 34. All right, let's look at the next one, number 35. 35, calculate the instantaneous speed in meters per second at the 10-second mark for a car that accelerates from 2 meters per second from a position from rest. Okay, I'm gonna see if I can fold over the paper in here. If I can use the paper. All right, let me write down what they told us. I call this translating the problem. I'm gonna have to read it again. Here we go. Calculate the instantaneous speed. We want to know what the speed is in meters per second. At the 10-second mark. Okay, what does that mean? Well, let's say it started from 0 and at 10 seconds. So delta t, okay, this is number 35. I know that delta t is 10 seconds. Okay, see, I know that looks like a little 5. 10 seconds. It said a position of rest. Oh, it started a position of rest. That means my V initial is 0. And then I know that it got up to, oh, we want to know how far did it get up to? It tells you the acceleration. Here it tells you the acceleration is 2 meters per second squared. 2 meters per second squared. And they want to know what is the final velocity at that instant. I'm going to call it the final velocity. That's what we want to know. What is the final velocity? So another equation for this one. They give you a shortcut equation, but I want you to understand why that shortcut equation works. So I'm going to give you the real equation. V final is equal to V initial plus A delta T. Okay, so whatever speed you start with, you got to add the acceleration times the time. Now, I believe that this should make sense to you. Let's go back to that chart that I had, new share. Go back to that one again. Let's go back to here. Okay, hopefully you can see that. So I believe that you can see that V final, by the way, here's the equation that we're talking about now. Bring that up a little higher. V final is the initial velocity plus acceleration times the delta T. So let's look at this last hour. The last hour was 65 miles an hour, but let's see, you didn't know. We do know that every hour, I didn't write it down for you, is 5 meters per second squared. Since this typewriter can't let me do the, oh, actually it does, hold on, it does. I can do 2 and then make this be a superscript. Here we go, superscript, there we go. All right, so I know that my acceleration is 5 meters per second. Ay caramba, sorry you guys, 5 miles per hour squared. This is hours in this case here. Every hour you drove another 5 miles per hour faster. So every hour, that's why it's miles per hour or miles per hour squared. All right, so there's my acceleration. Here's my equation. I believe that you guys should believe by looking at this. So if I started at 50, okay, the question is how far were you driving in the 4th hour? So 3 hours later, okay? So 3 hours later, well, we take the acceleration, which is 5. There's A is 5. And we're going to put 3 hours. 5 times 3 is 15. Add 15 to 50, and you get 65. Okay, so let's look at that again. Let's see here. Okay, so V initial here is 50 miles per hour. I won't put in units right now. And we know the acceleration is 5. Oh, I better put it 5 miles per hour. So for 3 hours, if I 1 hour, here's 1 hour later, here's 2 hours later, here's 3 hours later. So I put 3, here's my delta t, 3 times 5 is 15, and I add it to 50. So 50 plus 15 is going to give me 65. Okay, so that's this equation right here. So notice in the problem they gave us, the VI is 0. Okay, so let me go back to that one again. Share again, and I have to go over here. So they threw that equation to you saying the instantaneous is just A delta T in the book. And I want you guys to understand where that came from, and this is where it came from. So they gave us that the V initial is 0, so this whole part here goes to 0. So now we know that the V final is just A times delta T. The acceleration is 2, that's what we plug in there, and the time is 10 seconds. Time is 10 seconds. So let's look at our units. I got 2 meters per second squared, and I multiply that to the 10 seconds. There's my time, 10 seconds right there. 10 seconds. Now, eventually you guys should see that one of the seconds cancels out. But so far, let's say I don't see it yet. 2 times 10 is 20. So I'll have meters times seconds all over seconds squared. All right, so I know it's 20. So let's look at this part right here. So I have meters times seconds all over seconds times seconds. Now I can see that one of my seconds cancel out, and I end up with just meters per second. So this is equal to 20 meters per second. And there's my answer. And that's for number 35. Okay, so I'm going over problems, but I got to explain the equations so you know exactly how to use them. All right, let's look at number 36, which should look very similar. Hold on my paper. Here's number 36. All right, hopefully it's big enough for you guys to see. It says, calculate the speed in meters per second of a skateboarder who accelerates from rest for 3 seconds down a ramp, acceleration of 5 meters per second squared. If I haven't told you guys yet, I want to make sure, I tell this to honor students all the time, I want to make sure you guys are comfortable with reading a problem more than once. Why? Because sometimes they're long. And I have a master's degree and 2 bachelors, and I have no problem reading the problem again and go, wait, what? So I want you to feel real comfortable, go, that was a lot of stuff. So let me see what I got from here. Something's from rest. Okay, something started from rest. So I'll start with, I know that when it's at rest, it's not moving. So we'll say V initial is 0. And they want to know what the speed is. Okay, they gave us the initial. They want to know what the final velocity is. Okay, and they say 3 seconds. All right, now I know that the time, the delta T is 3 seconds. And they give you the acceleration. All right, acceleration is 5 meters per second squared. All right, that equation I gave you, V final is V initial plus A delta T. And yes, the V initial again goes to 0. So now we're left with V final, just the acceleration times the time. And what's our acceleration? It's 5 meters per second squared times the time, which is 3 seconds. 3 seconds. So I know one of my seconds cancels out, and I end up with meters per second. 5 times 3, 15 meters per second. Okay, so there it is. That one is number, 36. Number 36. All right, number 36. So now let's take a look at number 37. Number 37 should look very similar to you. Oh, I think I'll just flip it this way. Number 37. Here we go. Calculate the instantaneous speed of an apple 8 seconds after being dropped from rest. Okay, so we got the same thing going. The difference is now it's being dropped. Before we were doing one-dimensional motion side to side, but now we're going to be going vertically. Now, what's different about vertically? Y direction. This is in the Y direction. The difference is the acceleration, if you're on planet Earth, is always the same. It's not going to change. Acceleration due to gravity, pointing down. That's why when I drop my pencil, it goes down. It doesn't fly up. It always goes down. Acceleration due to gravity is always pulling it down to the center of the earth. Acceleration is negative 9.81 meters per second squared. Always pointing down. In the conceptual, we're going to let you guys round that off to negative 10 meters per second squared. Acceleration due to gravity. Sometimes you'll see this just written down as a little lowercase g. Okay, all right, so why did I tell you all that? Well, because in the y direction, remember I told you v final is equal to v initial plus acceleration times delta t. If you're in the y direction, now this guy is always acceleration due to gravity, which is negative. It's always negative. All right, so now let's read the problem again. Here we go. Calculate the instantaneous speed of an apple 8 seconds after it's being dropped from rest. All right, let's see if I can turn the paper this way. Okay, it's being dropped from rest. So I know that my v initial is 0. How convenient. And it wants to know what the final velocity is. That's what I want to know. What's the final velocity? And I know that that time that passed is 8 seconds. 8 seconds. All right, now they don't tell you, but you need to know or assume that this is happening on the planet Earth. If it's happening on the planet Earth, then I know my acceleration due to gravity is always negative 9.81 meters per second squared. But in this class, we can say, hey, that's about negative 10 meters per second squared. All right, so now we go back to that same formula we used before. V final is equal to V initial plus A delta T. All right, here my V initial goes to 0. How convenient. So now I have V final is equal to A due to gravity times delta T. Times delta T. Now notice they tell you GT. Well, yeah, because I told you acceleration due to gravity is often written as a lowercase g. Okay, so we got to plug that in. It's always negative. Remember, it's a vector, and it's always going down. So my vector is about 10 meters per second squared. And I multiply that by the time, which here is 8 seconds. 8 seconds. And again, my seconds, one of them cancels out, and I end up with meters per second. So it's negative 10 times 8, which is 80 meters per second. Now, why is it negative? Because it's going down. We dropped this apple, and it's falling down. So the velocity is pointing down, and that's why you have this negative there. All right, that's good. That was number 37. Let's go to number 38. I'll flip the paper over this way. Let's go to number 38, and we're doing more vertical movement. There we go. On a distant planet, and what does that tell you? On a distant planet, we're not on Earth anymore. So the acceleration is not going to be negative 9.81. Apparently on this planet, it has even bigger. So we're going to write that down. Let me read the whole problem. On a distant planet, a free-falling object has an acceleration of 20 meters per second squared. Calculate the speed an object dropped from rest on this distant planet acquires in 1.5 seconds. Whoa, that was a mouthful. So again, feel comfortable? Read it again. Calculate the speed. Oh, it was dropped from rest. Okay, so I know it started at 0. So it must want to know the final velocity. And it wants to know it after 1.5 seconds. Okay, let's write that down. Translate, translate, translate. First thing I know is that it starts from rest. That's a good place to start. Oops, why not? V initial is 0. And it has acceleration. Now, interesting, I told you if it's going down, then it has to be negative. Well, that's true here too. Acceleration due to gravity. As a free-falling object, because that's what a free fall is, another way of saying it, falls down due to gravity. All right, and it wants to know what the final velocity is, and it tells you the time. Time is 1.5 seconds. You can write an S. My S's are ugly, so I don't. Okay, so let's do the same equation again. V final is V initial plus A delta T. And how convenient, yet again, the V initial is 0. Okay, so we end up with V final is equal to A delta T. Now we can plug that in. A has got to be negative. You've got to remember, if it's acceleration due to gravity, that's what's making it fall down. It's got to be negative. So I have negative 20 meters per second squared. And they told me the time is 1.5 seconds. One of my seconds cancels out. And I have 20 times 1.5. So that's 20, and then half of 20. It's going to give me negative 30. You can use your calculator to prove this. Meters per second. And yep, it's negative because my object is falling down. Okay, very good. All right, so again, read that question more than once if you need to. The longer the question is, the more likely it's a good idea to read the question. All right, let's do the next one. 39. I can start with a new piece of paper. No, I got this one. A skydiver steps from a high-flying helicopter. If there's no air resistance, how fast would she be falling at the end of 12 seconds jump? All right, so this one, I have to introduce you guys another formula. Let me switch to that other page here. New share, the one I made for you guys for this video. All right, here we go. Just scroll down. What you're going to notice, these are called kinematic equations. All of these are kinematic equations, kinematic meaning it's moving. And so I wrote the first one down for you. The change in displacement, delta x, that's if you're going side to side, is the v initial times the delta t, how much time went by, plus half the acceleration, and then you take the time and square it. So that's for the x direction. This equation is for the x direction, which is also true, similarly, in the y direction. It's the same equation. So the v initial, your initial velocity times how much time, plus half of your acceleration due to gravity, and then the time squared. All right, so again, acceleration due to gravity is negative 9.81 meters per second squared. And in this class, we're just gonna round that to negative 10 meters per second squared. So this is the equation you want to use. Now notice, most of your problems, your v initial is going to go to 0. So this part right there is going to go to 0. If your v initial is 0, anything times 0 is 0. So that part goes away and you're just left with that 1/2 acceleration delta t squared. Note that the acceleration due to gravity is always going to be negative because that's what makes it fall down. All right, so let's go back to our, all right, let's see my share here. Getting better at how to do this. All right, so let's look at this one here. This one is number 39. Number 39, we're still on page, oh no, we're on 65. Okay, we're almost done now. Number 39. All right, hopefully you guys can see here. A skydiver steps off a perfectly good plane, or helicopter in this case. And when you just step off, you can assume there's no velocity. Oops. So you weren't like running and had a velocity when you jumped off the helicopter. So if you just step off, it's the same thing as dropping something. So your initial velocity is 0. So that's important to know. All right, how fast would you be falling? How fast would you be falling? What does that mean? That would be a speed. How fast? But it's velocity if you're going to show direction. And we are talking velocity here. How fast you're falling. So we want to know what v final is again. And it tells you 12 seconds. So we know delta t is 12 seconds. All right, now we also are going to assume we're on the planet Earth. Somewhere in the planet Earth, we're jumping off. And so our acceleration is giving negative 9.81 meters per second squared, even though you guys can round that off to about negative 10 meters per second squared. All right, so we want to know what the final velocity is here. So in this one here, because we're going in the negative direction, here we go. We're going to use final velocity because they gave us time. They didn't give us the displacement. That's why we're using this equation. We don't know what delta y is. We're using a delta t instead. So we have to use this equation. I'm going to go ahead and give you the long one. T plus a over 2 delta t squared. Okay. Again, I just want you to know where these equations came from. I did prove all these equations to the honors class. So if you're interested, let me know and I'll give you the handout that goes over the proof. And I'd be happy to go over it with you if you wanted to. Okay, so v initial is 0. So this whole first term goes to 0 because 0 times whatever is 0. So we're left with V final is equal to A over 2 delta T squared. Notice that the book gives you, they didn't say distance though. They're saying how fast. So this is not correct, but okay, that's for a different problem. So here we go. So we've got acceleration, which is -10. So we're gonna do that, -10 meters per second squared divided by 2. Don't forget that divided by 2. And all that times, we have to square the time. This is where people forget. So make sure you square that time. So they told you 12 seconds. So we're gonna say 12 seconds squared. All right, now, how does that work? Notice that there's meters per second squared down here. So let's just look at the units. And here I had meters per second squared. That's this acceleration. And now I'm gonna have seconds squared. So I'm gonna multiply that second squared, and then my second squares cancel out, and I end up with meters. Whoops. Meters per second squared. Looks like I might have, what number are we doing? I always get confused. We're doing number 39. Number 39. Oh, there we go. Okay. Meters per second squared, meters. All right, so that's giving me the distance. I really wrote this down for you guys wrong. This was delta y. Delta y. This is how far did they go? How far did they go? So let me go back to showing you guys the equation. All right, go back to that equation because I did give you the equation correctly here. There we go. So this is delta y. That's how far did that person fall down. Okay, how far the person fall down. I wrote the wrong parameter there. So it's like I'm solving something else, but we're gonna finish it though. All right, so how far? And notice how I figured this error out because my units, this is why I always include my units. If you do your units, you'll know you're doing it right. My second squares cancel. I went, hold on a minute, that's delta y. So that's how far this person is gonna fall. All right, so delta y, the distance in the y direction. So I know 12 squared is 12 times 12 is 144. So I end up with -5, 10 divided by 2, 5 times 144. 5 times 144, and that gives me 720 meters. Notice I have negative. That makes sense because I went down. Negative, I went down. Okay, so I taught you something else, but really they're asking you for how fast you were going. How fast, again, I want V final. So let me do this here. V final is V initial plus A delta T. Our V initial is 0. So again, I'm gonna put in here -10 meters per second squared times the time is 12 seconds. One of my seconds cancels out. And I'll end up with 10 times 12, which is 120, -120 meters per second. All right, so maybe it was my Freudian way of wanting to teach you a different equation that tells you how far they traveled, which I believe is the next question. Oh, it is the next question. All right, so the next question here, number 40. Calculate the vertical distance an object dropped from rest would cover in 12 seconds if it fell freely without air resistance. No wonder I thought these two problems were the same. I read this one wrong. So it says, how far would you go if you fall from rest and you went for 12 seconds, 1, 1,000, 2, 1,000, 3, 1,000, until finally 12 you hit the ground. So how far did you go? This is the equation you use, this equation that I gave you right here. Now notice this problem here is also 12 seconds. So this problem here, we already solved for you first. So let me write it a little more neatly. Again, delta y, the change in vertical distance is equal to the initial velocity times time plus the acceleration divided by 2, and then the time squared. This whole first part goes to 0 because you fell or you dropped it. I'm telling you it's 0. So we end up with the vertical distance is your acceleration over 2, and then you take the time and you have to square it. So let's continue here anyway. -10 meters per second squared I'm going to put all that divided by 2 because it doesn't matter if I do it right away or at the end. And then I have to multiply 12 seconds squared. Okay, so let's do that. Negative 10 meters, I'll put the units last, times 144, all divided by 2. And that also equals, what do we get here? 720 meters, and it's negative. Okay. All right, so I guess I was solving the next problem first. So you notice that 39 and 40 can both be the same problem. One of them says how fast were they when they landed, and the other one is how far did it drop. All right, very good. Last problem. Let's do the last problem. See if I can still use this piece of paper here. It says an apple drops from a tree and hits the ground in 1.5 seconds. So this is something can actually happen in your backyard if you had an apple tree or whatever kind of fruit you have. If it takes 1/1000 and then half a second to hit the ground, then you can figure out exactly the height that it fell from. All you had to do was time it, and it's using the same equation. All right, so we have the height in the y direction is equal to v initial delta t plus a over 2 delta t squared. If you're going to ask me, do I have to include this part? I would say, no, you don't. My honors people do, though. Okay, in this case, this part goes to 0, so you can go right to, because the reason I don't like this equation is because this is only true if the initial velocity is 0. Okay, it drops from a tree, then I know drops, there wasn't an initial velocity, so the initial velocity here is 0. Okay, and I know that delta t is 1.5 seconds. 1.5 seconds. And I know it's on planet Earth. I'm assuming this is happening on planet Earth. So I'm going to go ahead and round up to 10 meters per second squared. Okay, so now we can plug that in. Negative 10 meters per second squared divided by 2. And then I have to take my time and I have to square it. So this is the part students make mistakes. They'll write the square, but then they don't do it. So let's do that with the calculator. Make sure you guys know how to do that. I always do the cute stuff, the tricky stuff first. Why? Because it's done. Let's do that. On my calculator, I'm going to say 1.5, and I look for that square. Where is it? Where is it? It's a little button. There it is. See the square red button right there? So I hit the square red button, and that gives me 1.5 squared. There we go. What else do we have to do? We have to multiply that by 10. Now you can say negative 10. I'm just going to remember that it's going to be a negative answer. Times 10 divided by 2. There it is. So it's negative 11.25. Negative 11.25, and it would be meters. That would be the answer. Now let's see if I wanted to use the negative in here. How would I do that? 1.5 squared. I probably want to say times, and maybe I would put it in, well, let's see if I don't. I just say negative 10, all right, and then divided by 2. There it goes, negative 11.25. There you go. And that's it. So hopefully that helped you guys to be able to do your homework. That was number 41. Yeah, make sure you know how to do these because this will be on the test. I always pick problems that we've already gone through together, so all you have to do is practice it, and then you get comfortable. And I'm telling you this so that you know where the equation comes from, all right? So that's all I have for you guys. So see you next time.